talking about today, which is about as good as it gets in the future of life science. So just another minute and then we'll get started.
Wonderful.
Okay, I want to introduce my guest and author of a notable book. The book is called On the Future of Species. It's a big title. And the author is the co-founder of Genero. He's a molecular biologist, and his company Genero is really into synthetic biology. And he's written quite an extraordinary book about ABI. And people know about ASI, the artificial superintelligence, and AGI, artificial general intelligence. But here we're going to be talking today about artificial biology or biological intelligence. And this book really takes us through that convergence of AI and biology, state of the art and beyond biology. And actually, Adrian, you gave it several terms along the way, like RT-evolution, the second genesis, post-Darwinian, refactoring, programmable biology, the molecular Gutenberg press. You're basically, all these terms are getting at this monumental shift. So, that's how you frame it. Maybe you can give us your sense about the overall message of what you're getting at here.
Thank you, Eric, and thanks so much for inviting me onto your show. And thanks to everybody who's listening in today. Very decent of you to do so. I think you can summarize it in one very simple way, Eric. Right, that you can divide the modern history of biology into three clear phases. Right, the reading phase, the editing phase, and now the writing phase. Right. Well, you could also call that the authorship phase, right? And the reading phase was where we just document what evolution has handed us on a plate, basically. We just observe nature. And over most of the history of science, that's exactly what we've done. We've just documented things, we've catalogued things, we've taken things apart in the Baconian tradition, right? But that's kind of pretty much all we could do. And reading genomes, sequencing was the kind of ultimate kind of version of observation. It's observing DNA sequences, which are kind of the ground rules, if you like, for building a living thing, right? And then, of course, more recently, in this wonderful innovation of genome editing, right, which started off with zinc fingers and various other platforms, and then kind of talons, obviously, and then CRISPR, which kind of democratized gene editing. Anybody could do it. You could do it in your sitting room at home, and people do, as we know, right? But you know, writing life, authorship is something totally new. This is extraordinary, right? Because all of a sudden you move from a situation where you're taking a document, a genome, and you're redlining it, right? That's editing, right? You're taking a pre-existing work, a script, and you're editing it. But now you're going to a situation where you're not editing something that pre-exists. You're reimagining something, right? You're literally taking a blank piece of paper and you are writing the narrative. You are becoming Dostoevsky. You're becoming E.M. Foster. You're becoming Mark Twain, right? You're writing a new narrative. This is something qualitatively different to either reading or editing. And this is the new era of life that we're entering. And how do we do that? Well, we do that by unpicking the generative grammar of life, right? Because biology has a language, and it has a grammar, just in the same way that English has a grammar, or German has a grammar, or Spanish has a grammar. And if you want to write utterances, grammatical utterances, you need to understand that grammar, right? So modern biology in this phase transition, not only in the history of humankind, but in the history of life on Earth, is about this new convergence of the ability to design life using artificial intelligence. And that involves unpicking those grammatical rules, the patterns in biology that we can't see by eye, and then coupling that to a kind of printer, if you like, a way of constructing DNA at scale and turning those designs into physical reality.
Right.
That's what my book's about.
Yeah, no, I think it's fantastic because before we get to the authorship writing end of this, I want to you justify why we need to do it or we can do it. And I love some of the ways you get to the fact that this Darwinian natural selection isn't as great as a lot of people think. Because, for example, we have a spine that isn't really set up very well for humankind. We have, a 26 bone foot that isn't right. We have a recurrent laryngeal nerve that is circuitous. Wisdom teeth I wish I never had. We have all these things that you would, because the Darwinian story was one where, like, the house kept getting remodeled and then it became kind of an ugly house because it was, and you get to the spaghetti code, if you will. Um, can you take us through the fact that we could potentially do better than, I mean, most people would accept that it's as good as you get, natural selection. But we also know that there's trade-offs. So, for example, if you have a hemoglobin mutation that makes you resistant to malaria, it makes you more susceptible to sickle cell. So we have this pleiotropy of all this natural selection too. So maybe you can take us through the rationale that maybe this post-Darwinian ABI can be better than what we've gone for the last 4 billion or whatever years.
Yeah, I mean, first of all, as you know, all life is rooted in a universal common ancestor, right? So it is a tree of life, literally, because there is a lineage, and it can be traced, in theory, all the way back to the primordial soup, however long ago, approximately 4 billion years ago, right? And Yeah, look, evolution's done a pretty good job, right? It's created us, right? And
Yeah.
that's not a kind of trivial achievement. At the same time, evolution, if it were a person, would be kind of irritating because evolution would be that kid in class who's kind of a bit lazy and just does what's good enough, like whatever works. If it works, hey, that's good enough, right? And that's how evolution operates. It just takes a solution and then the next solution. It doesn't really optimize, but it just does something that works, right? Whatever works. And the problem with evolution is it can't just take a design, take it out, take it into the garage, reconfigure it, and then put it back in the air. No, the aeroplane always has to be in the air. And that's the problem that evolution has, right? Also, as you go down a certain route, I mean, it's like one's life. Every decision you make opens doors and closes doors, right? And evolution's been doing that for 4 billion years. So it's cut off huge swathes of possibility through every decision that it's made, right? Now, imagine now that rather than having to build upon the tree of life, you could actually dissociate from history, from what's all the designs that have come before, and suddenly enter what I call, actually, I don't use this phrase in my book, but I've developed it since my book, what I call the forest of life, right?
Mm.
And these are all the possible trees of life which time forgot, right? All of a sudden, the ability to write genomes from scratch enable total reinvention. So imagine how crazy it would be, Eric. Like if you wanted to build a modern day laser printer, imagine if it had to incorporate the good, you mentioned the Gutenberg press. So imagine if you had to evolve a modern day laser printer from a Gutenberg press. Imagine
Yeah.
how crazy that would be, right? Imagine what that would look like. In fact, I did get ChatGPT to imagine what that might look like, and it's kind of a weird contraption of wood and bolts and modern laser printer parts, right? And that's the way you should think about human biology, or indeed the biology of any species. It's this kind of anachronistic structure which has just been cobbled together over time, and there's a huge amount of historical contingency built in as well. So the end result is really pretty random, and suboptimal. And it's a little bit like you must have visited Rome at least once in your life, right? If you go to Rome, it's a charming city and you see ancient Roman forums fused with medieval buildings and modern buildings. And aesthetically, it's incredibly charming. And that's why we all love going to Rome. But it's a nightmare to live in Rome if you're if you're a city planner. Those streets were built for chariots, not for tourist buses, right? If you try and put in a subway system, you keep hitting archaeological sites. You can't do anything, right? And again, the human body is full of these kind of anachronisms from the past. And I like to think about human disease as being caused by those anachronisms, things which were relevant long, long ago, but have zero relevance today, but they kind of interfere with our biology. Now, let me give you one very good example, right? It was recently shown that when you kind of mapped out the GWAS hits for schizophrenia, that one of the candidates was a complement isoform, right? And it turns out that evolution has designed this protein in such a way that it has two totally different functions, right? One is in the immune system because complement's part of the innate immune system, but that same protein was also lazily subverted by evolution to perform a totally different function, which is synaptic pruning, right? So now you have two critical functions being subserved by a single protein, which can't be optimized to do either properly because it has to do both, right? And that's a perfect example of how evolution just kind of runs with whatever works because that worked, but it's suboptimal, right? So imagine if we could now go back, redesign, and now split that function into two separate proteins so that each could evolve independently and be perfectly optimized for each of these totally different roles, one in immunity, one in synaptic pruning. And that's just a kind of simple example of how the ability to engineer biology could actually help us to get rid of some diseases, for example.
Yeah, in the book, you use the term anti-orthogonal in that regard, whereas engineering, like a plane, they have modular parts that are not interdependent, and that's what
Yeah.
advanced just described, and I think it's a very nice explanation. Now, one of the things that I want to get into, and you already touched on this, I like your new term, the forest of life rather than the tree of life, because that gets us from Fred's library, Fred Sanger, who had all the combinations of nucleotides that you could imagine, to a new world where there's no limits. There's potentially any construct. And back when Venter did the mycoplasma mycoides, where he basically booted up in a cell a synthetic genome, that was back in 2016, I think. Right? Was that the first time that we saw this phenomenon?
Yeah. Well, I think, Venter obviously played a key role in the history of synthetic biology. He's a true visionary and pioneered the field in many ways, along with a few other people like Jeff Bucher and George Church. But basically, up until now, most of synthetic biology is essentially copying nature. So, we made artificial genomes of viruses and bacteria, and then Craig's actually managed to create a new species by changing, one species of bacterium into another by removing the original genome and putting in a new one, right? So he used the cell as a kind of chassis, and thereby showed that the genome really was acting as a program, a bit of software that could be put into the hardware, which was the cell, and then run on that little micro or nano computer, right? And that was a very important demonstration, right? That this kind of computer software analogy, right? But up until now, without in any way demeaning those achievements, right, we've essentially been plagiarizing nature, right? We haven't had the ability to reimagine nature. I mean, we've changed it a little bit. We can fiddle around with the order of genes, or we could put in watermarks, or in the case of the yeast synthetic yeast genome project, put in mechanisms to scramble genes or put all the tRNAs onto a separate neochromosome, right? But fundamentally,
Yeah.
we're still kind of recapitulating different iterations of natural designs, right? But I think where we're going now with the work of people like Brian He at the Arc Institute in Stanford and genome language models like Evo1 and Evo2, we're actually getting to the point where we won't just plagiarize nature. We'll actually be able to use AI-driven designs to change nature and generate new genomes which have never existed previously in nature. And Brian's recent demonstration that he could make a Phi-X, which only had 93% identity to the wild type, which technically meets the criterion for a new species, suggests that that was indeed the first ever totally new biological entity, because it's not quite a living thing about a virus, right? But the first ever human or computer created living entity, right? And obviously there's a big difference between a virus and even a bacterium, or a kangaroo, or or a koala bear, right? But what it means is we're on the mountain, we're on the ski slopes, right? But we're on the kind of the kids ski bump, right?
The
But,
bunny.
but we can see the T-bars and the chairlifts and the cable cars that lead us up to higher ground, right? And eventually, I believe, we will master the generative grammar of life through the use of AI, generative AI, genome language models, which interrogate increasingly more complex, sophisticated, and nuanced databases. And we'll have, we may not have all of the grammar to speak totally fluently, but we'll be speaking pretty well. So we'll be able to write biology in the same way that we author books today in different languages.
Yeah, I mean, I think this is what you're bringing up is so important. And Evo and Evo 2 are kind of great exemplars of this large language of life models. There's been a flood of them, but the whole point is that we're gradually getting this language of life in understanding, as you say, the grammar, the decoding, deconvoluting it, because it is such an extraordinary complex thing. Now, um, I did want you to comment, because this isn't quite the same what you're talking about in terms of the grand synthetic biology, which we're going to get into in a minute. But in recent days, the internet lit up because there was this Australian tech fellow who had a sick dog with cancer. And he decided to use digital biology, first with ChatGPT to design the experiments. Then he went to the local university in Australia, in New South Wales, and had the dog sequenced. And then he used AlphaFold and Grok to design a bespoke mRNA vaccine, which he then administered to his dog, who's apparently the dog is doing really well. Nothing else helped the dog, and now the dog is full of pep and back to normal. This is a big feat of a citizen scientist, not a biologist by any means, and using 3 different major AI tools. And this is really interesting, and because it's digital biology. It's really a very much a part of what you're into in the book. Maybe you could just comment on that.
Yeah, that was actually obviously a remarkable story, right? And it kind of shows you just how well these chatbots perform. I mean, how extraordinary they are. They really are quite extraordinary, right? And it also shows how we're moving in a direction where the ability to program biology is going to become increasingly democratized. That's a good thing. It's also kind of scary, right? Because it means, unlike nuclear technology, which was kind of safeguarded by very, very few individuals who had the resources and know-how to manipulate that technology, biology is a technology which can be democratized and is being democratized and will be in the hands of many, many people before too long, right? So I mean, this was an extraordinary achievement, and what an amazing imagination this guy had to do that, right? So, I mean, all credit to him, and I'm so happy for his dog. His dog benefited from this, right? And of course, with technologies like Sidewinder, developed by my co-founder, Genero Kaihang Wang, we can actually build these vaccines in like 48 hours. At the moment, cancer neoantigen vaccines for humans, which the data is looking pretty promising actually in some particular tumor types. But right now, you can take 8 to 12 weeks to turn those vaccines around, right? But Sidewinder enables those vaccines to be made in about 48 hours. So, it's hugely impactful because obviously the patients are progressing and there can be manufacturing failure and so on and so forth. So I think that, the story just provides an incredible example of what's possible, and also how, biology is being democratized in a way that was hardly imaginable even a few years ago, right?
Yeah, and also sets up for a potential downside we'll get
Yeah.
into in a. But I do think that, by the way, the Sidewinder uh, explanation in the book is very helpful because, as you say, it just accelerates this whole thing in a remarkable way, which we're going to see a lot more of in the future. So what we have now is that there's the good and bad that could come out of this powerful convergence, ABI. Um, and one of the quotes in the book, which is for me memorable, it should be possible to meet most of humanity's needs through biologically inspired designs to solve many global problems, revolutionize healthcare. I'm kind of interested in that, and extend human lifespan. and create other organisms to order. So, this is something which you also said the ultimate goal of clinical medicine is to liberate humankind from disease. Uh, so that would be, of course, a fantastic outcome from this new capability. Is that realistic? Can we actually? Obviously, it's not a one and done thing. This is going to take decades. But are you optimistic that we will make big advances with synthetic biology (ABI) for diseases?
I'm totally certain of that, Eric, because we're like a kind of gene kit, like you said. It's not an orthogonal kit because the parts kind of network together, right? Some parts behave like components, and obviously the 7,000 or so monogenic diseases can be treated like components and fixed pretty easily with gene replacement or gene editing, right? But the greater majority of diseases are complex, multifactorial, and that's environment as well, as we know, right? But to understand those complex diseases where genes have many genes have tiny effects, we're going to have to reverse engineer the grammar of life and understand how ungrammatical statements generate disease. Now, we weren't unfortunately born with an instruction manual of how we work in our hand, right? But we have to be computable. I mean, to me, that's a fundamental premise, which not everybody agrees with, right? Some people don't think that biology is predictable. I think it is, right? And I think, part of our job in the next 10, 20, 30, 40, 50 years is to reverse engineer our instruction manual, right? Using AI and using the ability to construct new genetic circuits and bits of chromosomes and so on. Obviously in animal models and cell models and so on and so forth, right? But I believe that we should be able to reverse engineer how we work and therefore how our operations go wrong, i.e.,
Yeah,
how we generate disease. Now, obviously, I'm not trying to simplify disease to just being genetic because it's multifactorial. We know there's epigenetics and learning, development, there's culture, there's our environment, our diet, our microbiome, all of those things. And in my book, I actually use the term informiome to kind of democratize and, all the information that makes us what we are and contributes to disease. But I still fundamentally believe that if you can compute the genome and reverse engineer it, you're going to make huge inroads into human disease. Now, would
yeah,
we ever consider rewriting parts of the human genome? That's a tough question, right? Because that assumes that we're fully computable, right? And
yeah.
if we're not fully computable, it means that rewriting ourselves is a really, really risky business.
Yeah, I mean, that's where I'm more circumspect of how difficult this is because I've watched the genome editing era that you
Yeah.
mentioned, and here we are 12 years into CRISPR, no less the other um, nucleases that annotated it. And, we have CRISPR 1.0, and, it
Well,
takes a time. And those are the monogenic diseases that are the most amenable to editing.
you know,
So I'm having a harder time. I think you may be right for certain polygenic, which are most diseases. But as you know, this is a 3D genome, and you touch one part and you got ripples everywhere else. And as you said, there's multiple layers and side chains and whatnot. This is a formidable task. I mean, what I was going to say, Adrian, I think the ability to work on organisms that eat our carbon dioxide or plants that are more better sustainability, those probably would be better suited for triumphs, don't you think, for synthetic biology and ABI?
sorry, better suited for what, Eric? I didn't get the
Uh,
last.
if we use plants that we make them, just
Oh,
function, and
yeah.
we design organisms to change the climate crisis.
Yeah. Let me just first go back to your other point, which is about, that gene editing hasn't really delivered. I did my PhD and postdoc with a guy called Cesar Milstein, who invented monoclonal antibodies, right? And I remember sitting in my office with Cesar, right, in the 1990s, and, him sitting there, not being depressed, but a little bit, miserable at times, because he was getting so much criticism. You promised us that monoclonal antibodies were going to change the world. And here we are in 1995, and there's only two approved drugs. What's going on, right? And of course, they were totally wrong. It just took a little bit longer
Yeah,
than we thought, right? Things take time, but
yeah,
we're so impatient, right, with everything, right? The two problems with gene editing right now, it's not there's no kind of conceptual philosophical problem. It's just one is the cost of it, right? How do we democratize it? The second is that drug companies won't develop drugs for N=1 diseases, and people are addressing that now. Jennifer Doudna, Theodora, they're working on that with the FDA. That's great, right? Third, delivery, safe delivery, right? We're going to solve all of those problems, right? But then, as you also mentioned, right, that if you fix one thing, there are knock-on consequences, even with single genes, right? So sickle cell anemia, suddenly you're susceptible to malaria, right?
right,
Which is
right.
a big problem if you live in India, Pakistan, or Africa, right? So you're absolutely right that tinkering with whole genomes, is going to be a very complicated thing to do. But it may be actually that the whole way that we think about disease is wrong, right? And there've been some very interesting experiments, for example, where people, there's some network medicine, right? Well, paradoxically, you can cure a problem by damaging a network further rather than fixing it, right? And maybe we need to rethink how we think about disease. And I'm almost certain that, that, that will happen, right? Our paradigm may just need rethinking. But despite all the complexities, I'm still pretty confident that even if we are not prepared to rewrite the whole human genome or parts of it, that the insights that reverse engineering the grammar of life will give us will hugely help us to treat most common fatal diseases. And I think the successes we've seen, for example, in cancer, drugs like imatinib, cell therapy in lymphoma, checkpoint inhibitors in certain cancers. It basically demonstrates to us that cancer could eventually become like an infectious disease, right? That, there's no reason you need to die of cancer. There's no reason. And I'm pretty certain that most diseases will be, the peer untreatable will be treatable. But then we're going to get to that really thorny issue, right? When if we do manage to treat or prevent most human diseases, we get to this weird situation. Well, what next, right? Like, how long are we meant to live for as humans? What is human nature?
Yeah.
Are we meant to live for 100 years or 200 years or, and that's a whole nother philosophical issue.
Yeah, no, we won't get into that so much because I'm, much more trying to extend health span and not too worried about lifespan.
Yeah.
But your point about editing, now that we're in the base prime editing era, it's coming along. But as you say, getting delivery in vivo, getting the cost down. But what I'm trying to get at is, it seems to me that the great outgrowth of ABI, which by the way, most of the genome editing era wasn't with AI. There were no foundation models. There were no transformer things. You couldn't even imagine doing what you just said as far as working on the human genome without the AI to help deal with the immense data challenges, analytical challenges. So this is a big difference. But now I want to touch on the potential negatives. Now you do call for a global moratorium, and we shouldn't be messing with human embryos as was done in China. But obviously we have other concerns when you democratize this as far as bioterrorism, security, the ethical issues. Can you comment about that?
Yeah, in a sense, I mean, one of the main reasons I wrote my book is to kind of say, hey, this is a wake up call. This is happening. So it's already happened, right? This isn't the future. We're doing this now. And in fact, the final chapter of my book, chapter 12, is a manifesto for life. But I call it a sketch for a manifesto for life because I don't think any individual has the imprimatur or right to, to actually present a kind of manifesto in a kind of final format, right? So it's a sketch because it's a beginning. It's a tentative beginning, and I myself change my mind on these issues every other week, right? So but it is a sketch. But it was an attempt to create some kind of basic guardrails, some basic philosophical kind of signposts and foundations, right? And I guess it's definitely the case that we need to find a way and align at a civilizational level globally, align on a way to use these technologies safely, wisely, responsibly, equitably, and in a manner that benefits all of society, and in a good way, right? And these technologies are dangerous, both they're both dangerous because of bad actors, whether they're individuals or nation states, right? But they're also dangerous because of the fact that we don't always realize how little we know about ecosystems, for example, are very, very difficult to model, right? And we may inadvertently cause great damage, right? So I think we just need to be really, really cautious about how we navigate this extraordinary new landscape that we've entered. There's tremendous opportunity to bring good to humanity, and there's tremendous opportunity to do bad. But the technology itself is morally neutral. I think that to me is clear. Fire is a dangerous technology, but you can cook your breakfast with it. It can keep you warm. The wheel, what a dangerous technology, right? But it's also pretty useful when you want to go on your driving tour of the south of France, right? And pretty much any technology you can think of is dual use, right? But the human imagination, takes us to these places which offer possibility to improve the experience of being human. And I think to deny that would be to deny our humanity. You can't put a kind of brake on our imagination, right? So we're always going to think of new things that are potentially dangerous. And it's up to us as a global society to ensure that we are responsible.
No, I think the way you handled this in the book, especially and as you just summarized succinctly now, is laudable because we're talking about two potent things that have converged: AI itself and the ability to write a genome. And then when it's like to the fourth power, because both of them have this remarkable potency, and now you're combining it in the form of ABI. But one thing, we go back to the end of disease story. It's pretty hard to imagine that we can do that with somatic genome authorship. We're going to have to remove the chance of cancer or a neurodegenerative disease. This is likely if we're going to use um, genome authorship and this molecular Gutenberg press. We're going to have to start to get into the embryo part, which is really when you change the human race. Would you agree? And that doesn't that make this a more formidable challenge?
Yeah, well, just to make it really clear, right now, I'm really not an advocate of germline editing or rewriting at all, right? And so I think any attempt to even consider doing anything in the germline, to me, should be, far, far away. That doesn't mean to say that some nation state somewhere isn't going to want to do it, right? But I don't see that happening anytime soon. There may be economic reasons, and those are probably the reasons that will drive people to do it. Like, it would probably consume most of the GDP of Pakistan if they wanted to treat sickle cell intergenerationally across the country. And there's a lot of people, carrying sickle cell trait, right? So I can't see how that's ever going to be, economically viable unless, we kind of progress quite significantly with the technology. But I think the point is that as we've discussed, right, that in fact, the human body metabolisms are not orthogonal, right? And
Mhm.
that means however much you can kind of pull apart functions, right? There's still always going to be a lot of interconnectivity. So Voltaire talked about the best of all possible worlds derived from Leibniz, right? And the point about the best of all possible worlds was that there was no single possible world. There was like
Right.
a whole universe of alternative best of all possible worlds, right? The point being that every world is defined by its own unique set of constraints, right? So you might be able to get rid of all disease and increase longevity, but that's going to have a cost, and we don't know what that cost is. But I can tell you almost certainly that there's going to be a cost. And what is it? What aspects of human nature will change in order to get rid of disease? What price are we prepared to pay as a species to rid ourselves of disease? And it might well be that we don't need to do this at genetic level at all, that the insights that we get from reverse engineering the grammar of biology can help us to manage disease in a way that doesn't involve germline genetic manipulation, right? Well, that may well be the case as well, right?
Yeah, I mean, I think if you can learn from the grammar that leads to a small molecule or not a permanent programmable feature is another alternative as well. This is so provocative. What you've done here is you made people think. Like you said, it is a wake up call because these capabilities are not going to go away. They're just going to get enhanced over time. So I wanted to say to everybody, we've got well over 500 folks joining here live. This is a really interesting book. I was an endorser. Many other people got behind this book, and I want to give you a lot of credit, Adrian. This was a lot of work that you did to put this together. Very thoughtful. Obviously, many people will challenge this because you're starting to get to a way out there in time when this could actually achieve some of the potential milestones that are enumerated in the book. The one that I am excited about, especially, is could this biological convergence ABI be a solution to our climate crisis? That
Yeah,
one seems really alluring. What do you think?
I think there are many ways in which it could, Eric. I can give you a number of examples, right? So one obvious example is the archiving of digital information. Right now we use by various estimates anywhere between 6 to 10% of global energy production on archiving digital information, and that's just going to increase and increase. So imagine if all of a sudden we could store that information in DNA. DNA
Yeah,
consumes no energy, zero energy. At Genero, we're still technically in stealth mode, so I can't say too much, but I can tell you we are working on that, right? And the ability of Sidewinder to make these really big pieces of DNA gives us a huge advantage over oligo-based DNA information storage, right? So we're really confident that this can be done in a very, very effective manner. So right there, you've just saved 10% of the world's global energy every year
yeah,
by
yeah,
storing in DNA and all the damage that that does to the environment. Let me give you another example. At Genero, we're only focused on really consequential projects of global significance. And another of our programs is around generating neochromosomes to reprogram the genomes of crops to make them drought resistant and heat resistant, to increase yields and pest resistance and so on. This is a whole different ballgame to editing, right? We're talking about reprogramming, right? And
right.
people say, oh, but people won't even eat GM modified. Why are they going to eat genetically reprogrammed crops? You know what? You may not have any choice because you
Yeah,
need to eat, right?
yeah,
And,
yeah.
and uh, the world's population is going through the roof. And the sad thing is, in order to sustain that, in the absence of a second green revolution, we're going to destroy all the wilderness remains in the world. We're going to chop down all the trees like they did on Easter Island, right? We're going to lose all of our heritage, all of the species that contain these secrets, earth secrets that can help us, right? If we don't find a way to improve the efficiency of food production, the future will be very bleak indeed, right? So for me, synthetic biology isn't a nice to have. It's actually essential. It's of existential importance for humanity's future, unless we just dramatically reduce the world's population, right? And stop producing greenhouse gases and so on. So those are two really clear examples
I
for
love
you
that.
right there.
To me, those are just extraordinary, and they're going to be helped by having this convergence, this ABI, as you describe it, not just the biological programming element. So, I just am wrapping up, Adrian. This really, you did so much work here, pull this together. It's very balanced. It's very futuristic, of course. Have I missed anything? I mean, we only had a limited time to discuss it, but I think it's something that anybody who's trying to think about life science of the future and how AI comes together, you're going to learn a lot and think a lot from what you pulled together in on the future of species, which that title alone should get people thinking. Anything that I've missed?
Eric, I think you've covered such a broad spectrum of topics. It's been great. All I can say is I've done my best to summarize what I think is a really, really consequential and unprecedented moment in the history of kind, history of life. I tried to write in a way that can by pretty much anybody. There's a lot of history and anecdotes in it, and I hope I've achieved my aim of making it really approachable so that everybody can understand what this is about and then participate in the debate and have their own voice and their own opinion.
Yeah, no, I think it is thoughtful, and you can tell that you were debating yourself at many points in the book. So it's very apparent. So thank you for joining. I want to thank all of the folks who took that time out of their day to get into this discussion. I saw a couple of questions that came across along the way, but we've got well over 560 some people that are part of this, and we'll have this archived so that everyone else can hear what we discussed and send in questions. And I'm sure Adrian will be fielding lots of questions about all the wake up call and topics that he really took us through in this new book. So, Adrian, thank you. Well, this is your third book. I don't know if you've got another one in you, but this one certainly is extraordinary. Thanks a lot.
Thank you, Eric. It's been such a pleasure. Thanks to everybody who's dialed in today. Really appreciate it.
All right, bye now.
Bye bye. Bye bye.